let me thank Julia and Oral for organizing these Science Saturdays, and the West High School for hosting this. So before I start, let me ask you guys a question. This is an important question. How many of you know what song was playing before? Yeah, see? That was, yeah, see, a lot of the people know, yeah. That was one of my favorite songs. I was just playing this, and Jay here tells me that was he was saying that was his youth song. So, how do I turn this on? It is on. I guess not. Well, anyway, so how many people do we have from middle school here, and how many from high school? Middle school first? High school? Yeah. More middle school than high school. Okay, so my name is Amit Goyal, and I'll say a few words about different kinds of solar applications and how solar cells and solar thermal can be used for energy. But let me introduce to you the main people that you're going to be interacting with today. So you're going to have projects that you're going to do on solar photovoltaics and solar thermal. And you will interact with the solar PV team. And if everybody's here, Nadia, are you here? No, Nadia's not here. Jay Jellison, Jay, can you just, yeah. Pooran, Joshi. Curt, Maxey. Curt's probably still, they're arranging a few things there. And Parans. And then you're going to do a project on solar thermal, and Joanna has put that project together. And so these are really cool projects that you will be working on today. So let me start out by asking you a question. So the question is, what are the two things that the sun gives us?
Heat and light.
Perfect. See? Heat and light, and that gives us solar energy. So the next question is, how much solar energy is there? Anybody?
There's practically as much as we could ever want coming out from the sun. However, most of it is not hitting the Earth, and that which is hitting over a wide area, so it is hard to collect.
Anybody else? That's a good answer. But if you look at the map of the world, there's tons of solar energy coming. In fact, there's so much of it coming that in 1 hour, more solar energy hits the Earth than is used by the entire world in one whole year. So there's tons of it that's coming out, right? And it's all green, clean energy. So
the problem with that analysis is that much of it is needed. You said the whole world, but you're wrong. All of technology uses it in 1 year. You must also remember that the plants are taking that light.
Right.
It's necessary.
No, you're absolutely right. You're absolutely right. So you can't actually harvest all of it, and that's why right now when you look and you ask the question, well, how much solar energy do we use today for all the energy needs we have? It's only a few percent. And so it's going to be a while before we can actually make it the dominant form of energy that we use for our gadgets. But you can ask another question. What is this solar energy, right? I mean, solar energy, you go out, the sun, it looks white, right? So what is the solar energy? So you've seen the rainbow, right? So you know that the white light can just like the rainbow, is formed when you have rain droplets, and you have this thing called refraction which occurs, that white light, which actually comprises of different colors, is refracted at different angles from 40 to 42 degrees when you go from one end of the spectrum to the other, just like white light through a prism would refract into different angles. But the sun spectrum is much broader than just this. So the sun spectrum is actually, if you were to plot it, it would be a bunch of wavelengths with this intensity, so it looks something like this. And so it goes from low wavelengths to high wavelengths. But then luckily, some of the low wavelengths actually are harmful wavelengths like UV, and the ozone layer kind of filters them out. We've got other filters for some of the higher wavelengths, and the visible spectrum that you see in the rainbow is just this wavelength regime from here to here. So the wavelengths that actually hit the Earth that one is really concerned about range only from a wavelength of 400 nanometers to 1 millimeter. So this is sort of the spectrum that's coming out from the sun, hitting the earth. So what are the solar technologies that we can think about? So you can think about simple things like daylighting. Daylighting and passive solar heating, which is sun coming into your house and giving the effect of light. Passive solar heating is using sort of the greenhouse effect to heat your house. Then you can talk about active solar heating, where you're heating, for example, water, creating hot water. And then there are the two important topics, concentrated solar and photovoltaics, that I will spend more time on. So daylighting, right? So you've got a nice set of glass windows here, and you can get the sunlight to come in, so you don't need to use a conventional light. Passive solar, again here, you can have sunlight coming in and heating the space that you are living in. And of course, these two applications have been used for centuries. Then there's this active solar heating, where you've got a collector. Basically, you've got pipes going through it, like this, which absorb heat. Water flows through it, or some sort of a heat exchanger fluid flows through it, and then it goes through this tank where you have cold water and hot water coming out. So this is like a hot water heater, right? Go ahead.
You can also heat food.
You're right. You can make a solar cooker out of it. In fact, you're going to make one of those today. And make s'mores, right? Joanna, there you go. So the two main things that, kinds of solar technologies which are of interest around the world, the first of them is called concentrated solar thermal power. So here what you're doing is you're using the heat that you have from the sun, you concentrate it down, heat some medium, and then convert the heat in some way into electricity. And I'll talk a lot about this. And the other is that you all are familiar with, photovoltaics or solar cells, where you're taking the sun's certain spectrum of light that's coming in, the photons that come in, and convert the light directly into electricity, right? So you use solar cells, I'm sure, and you've seen them in watches, seen them in calculators, and you've obviously seen things like this as you drive around. So let's discuss these guys in a little bit more detail, and then I'll come back to concentrated solar thermal. So the question you can ask is, what materials are solar cells made of? Anybody? So the answer is they're made of materials called semiconductors. So now obviously the question you're going to ask is, what are semiconductors, right? So, no.
Semiconductors are material that may or may not conduct electricity, depending on certain stimuli.
Good answer. And that is absolutely correct. But if you look at the broad classes of materials, you've got three kinds of materials. One are conductors, like copper wire, right? It's a metal, it conducts electricity very well. Then you've got insulators like rubber. They don't conduct any electricity, right? And then you've got semiconductors, which fall in between these two. So semiconductors are things like silicon, germanium, gallium arsenide are some examples. The important difference between these classes of materials is that the number of free electrons in these materials are different. And that's how they're broken up into these three different classes. Now, in any atom, when you have electrons in an individual atom, you probably covered this in your physics classes, that these electrons can only occupy certain energy levels. They can't just sit anywhere. They have to be in certain well-defined energy levels. And when they move from one level to another, it's called a transition. And there's an energy gap, right, that they have to cross. So when you think about different classes of materials, like conductors, insulators, and semiconductors, the obvious question is going to be, well, what is the electronic structure of these materials which makes them either conduct or not conduct electricity, right? So I told you that these materials can be put, all these electrons have to be in different levels. So in any solid, you have atoms which are linked together, and these electrons have to go into different bands. So if you plot energy versus distance here, all the electrons have to be in various bands. Now within one of these bands, the energy difference is low, but between bands, there's a considerable energy difference, and you need some energy to move an electron from one band to another band. So now you ask, well, let's say copper or a conductor like copper, what does it look like, right? So in a conductor like copper, the two most important bands that you need to think about at this level is one band is called the valence band, the other band is called a conduction band. That in a metal like copper, the valence band is completely full, and in case a band is full, electrons cannot hop. So the valence band can't do anything. But in a conduction band, you have free electrons and some empty levels. So electrons can go to empty levels and leaving a hole behind. And both of these free electrons and these holes can move around. And that is why a metal has very good electrical conductivity like copper, right?
Why?
OK, so it's because it's got a lot of free electrons here in one band. The minute you have lots of free electrons, they can move when you apply a field.
What do you mean of one band?
Right. So you have an atom. The atom has electrons around it, right? And these electrons can occupy certain energy levels, right? And these levels are called these bands that I'm talking about. Now, in case the band is half filled, right? And within a band, there's very little difference in energy. So you apply a small field, like a small electric field, like a battery or something, right? Then electrical current can flow because these free electrons can move. Yeah? So now you ask, what does an insulator look like? Something like rubber, right? So a rubber would look like this. All the valence band is completely full, but the conduction band is completely empty, and there's a huge gap between them. So in other words, in case you want to create a free electron over here, it's going to be extremely difficult. And without those free electrons, you can't get conductivity. So that's what an insulator is. So now you're obviously thinking, what does a semiconductor look like, right? So I already showed you the insulator, the rubber, in the last slide. So this is what a semiconductor like silicon looks like. In this also, this red valence band is full. But rather than have this very large energy gap between this and this, there's a very small energy gap. So even increasing the temperature or shining light, you can move one of the electrons from one band to the other. If you do that, if you move an electron from here to here, these electrons can move around then, and it creates a hole here, and that hole can move around here. So in semiconductors, you can control the conductivity like this. Of course, now you can think that you can control the conductivity by chemical doping. So you can take this semiconductor, and you can dope. Certain doping means you can add certain elements to it which have more electrons or less electrons, right? So silicon, right? Silicon is what's called tetravalent. If you add a material like phosphorus, it's pentavalent. So when you substitute a phosphorus atom in the silicon lattice, it creates a free electron. And when you have a free electron, because normally it should have 4, and now you have 5, these guys can move around and create good conductivity. On the other hand, if you put something like boron, which has 3 instead of 4 in silicon, it creates a hole. But these holes can also move, right? The reason why holes move, because electrons can come there, and they create a hole from where they left. So how do you form a solar cell? You take one p-type semiconductor, and you take one n-type semiconductor, one which has more electrons, one which has more holes, combine them together. What happens when you combine them together? You take a material which has more electrons, a material which has more holes, you put them together. The place where the more electrons were, they like to go to the place where the holes are, and they recombine. And when they do that, you start out with something which has more electrons, more holes, you put them together, the free electrons go to the holes, and they recombine there. But when they do that, they create a certain positive charge here, a negative charge here, or an electric field. Now when you shine light and move a free electron from here, or you create a free electron, it gets swept up by the electric field to create this current. So a better way of explaining that is in this video. You're going to see an n-type material and a p-type material, and I'll show you how what I just told you happens. Oops.
Electrons from the N side diffuse across the PN junction to the P side, and holes from the P side diffuse across the PN junction to the N side. The electrons and holes can then recombine. The result is a net negative charge on the P side of the junction and a net positive charge on the N side, creating a strong electric field across the junction. Now, when we shine light at our PN junction, an electron will be excited from the valence band into the conduction band, leaving behind a hole.
Right here.
This time, however, before the hole and electron can be combined to emit a photon, they are separated by the electric field created by the p-n junction. The negative electrons move to the positive region, and the positive holes migrate to the negative region. By separating the electrons from the holes, we have prevented their spontaneous recombination and loss of their excitation energy.
Right. So that's what a basic solar cell is. All solar cells have this junction of semiconductors, right? And so you shine light from one side, and you can pass a current, and you can light a bulb or anything else that you would like. So the next question would be, well, what materials are used, or what semiconductors are used for solar cells? And you've heard the word silicon a lot, right? So most solar cells that you see installed are made of silicon. This is crystalline silicon. Actually, it is what's called a single crystal silicon, namely all the atoms are arranged in an orderly fashion everywhere. Some of the cheaper ones are polycrystalline, means atoms arranged in different arrangements in different locations. And there's some thin films or really amorphous cells which have lower efficiencies. But there are other materials as well that are being used. You've probably heard of companies like First Solar or some companies like that where you talk about thin film solar cells, flexible solar cells. They're made of materials called cadmium telluride or copper indium gallium diselenide. These are compound semiconductors. And then you can have even more advanced compound semiconductors like gallium arsenide, which are used for space solar cells. And the reason why you use some solar cells for some applications and some for the other, because they have different efficiencies. And you want to use materials with higher efficiencies for higher end applications, and you use lower ones like amorphous silicon for calculators. So everything that I've told you would nicely be summarized in this video about what are solar cells and how they get the mission accomplished for converting sunlight into energy.
First solar cells were made of silicon, and today silicon makes up more than 3/4 of the rapidly growing worldwide photovoltaic market. But photovoltaic, or PV cells, are also made with other semiconductor materials. Why so many types of solar cells? This diversity is due to innovation. PV materials are improving, manufacturing costs are dropping, and PV applications are expanding. Balancing these three factors can meet demands for clean green power while creating more effective jobs. Innovation means improving photovoltaic materials. Every PV material absorbs sunlight differently depending on band gap, which is a unique electronic property of the material. Some cells absorb sunlight within the first micron of the material. Others need 100 times more material to absorb the same amount of energy from the sun. The sun's energy arrives as a combined spectrum of different wavelengths. Each color carries a different amount of energy. This makes solar cell design more complex. If the energy of the absorbed photon matches the PV material's band gap, then an electron-hole pair is created. If the photon has more energy, it still creates only one electron-hole pair, but the additional energy is lost as heat. If the photon has less energy than the band gap, it is not absorbed. Low band gap materials absorb most of the solar spectrum, creating many electron-hole pairs, producing a high current. However, PV cells with low band gap materials have a low voltage. High band gap materials absorb only higher energy photons, creating fewer electron-hole pairs, producing a lower current with a higher voltage. A solar cell's efficiency is the percentage of the solar energy shining on the cell that is converted into electrical energy. One way to increase efficiency is to use multiple layers to capture power from multiple wavelengths of light. Understanding the properties of each PV material allows scientists to improve designs that maximize the power of the sun. Innovation in cells can be made from materials such as cadmium telluride, copper indium diselenide, or amorphous silicon. These materials absorb light more readily than crystalline silicon, so they can be used in very thin layers that are less expensive to produce. Thin-film solar cells are generally less efficient than crystalline silicon cells, but they can be cheaper to manufacture because they use less semiconductor materials, which are grown on glass or flexible foil. Finally, innovation means meeting different applications best suited by different types of solar cells. Today, PV devices produce power to meet the needs of utilities, businesses, homes, and consumer products. Large-scale installations can use a range of highly reliable PV technologies. Solar-powered satellites are more sensitive to power and ground. These high-efficiency solar devices can accept higher material and manufacturing costs to get more electricity from less material. Flexible thin-film devices are being installed in innovative ways, including incorporation into structures of complex shapes. Photovoltaics are here and now, and the diversity of PV devices is advancing as scientists improve PV materials and develop new manufacturing methods. More solar applications are emerging as these innovations make PV more affordable.
Right. So if you were to look at all the solar cells that people have made around the world, and you saw what efficiency is the amount of sunlight shining on a cell and the amount of sunlight from that, what fraction of it is converted into electricity, right? And it's hard to see this plot, but this is actually the world plot of all efficiency records, because everybody's trying to fight and trying to develop a cell which can convert more electricity more sunlight into electricity. So at the high efficiencies, which are like 40%, these are all compound semiconductors, multi-junction that you saw on the video. You put different kinds of semiconductors together, right? The crystalline silicon are somewhere in this regime here. And all these thin film technologies are down below here. But all of these cells are more expensive than they need to be in case we want to use solar technology in lieu of what we currently get from the grid. And so we have to work towards decreasing the cost. But you can ask, well, in case you did have solar cells on your house, well, how would you couple that to the grid, right? Or how do you get electricity to your house right now? So this very quick, short video is going to tell you how that happens. So what you saw in the video was that when you install these solar panels on your roof at home, you can actually sell electricity to the grid.
Really?
And so that's cool, isn't it?
So how does it work?
Like you saw in the video. So the way it works is right now you've got these overhead transmission cables which give you, you've got this meter, electric meter in your house, and you're buying electricity from a utility company. You're paying for it, right? And if you install a solar panel, you use some of that energy, so you use a little less energy than you would otherwise need to buy, right? So that's how you can save money. And if you're on vacation somewhere, where you still have the solar panels in your house, but you're not using any electricity, so you can just sell it straight to the grid. And if you sell it to the grid, you get a credit. That's how your meter goes backwards, yeah?
How do you prove that you sold it?
Oh, you get credits in your bill. So yeah, you get a bill, right? And you say, okay, you use so much electricity, and this is per cost of electricity, so this is your bill is. When you get your bill, you'll see a credit, means you will see, right? Good. So
You could actually get like money with your bill.
exactly, there you go. Isn't that cool? Right. So as I mentioned to you, the solar cells are too expensive right now. So we have to do something to make their cost compatible with the electricity that we buy from the grid. So the Department of Energy in the United States came up with what they call the Sunshot program. So many years back, there was this Moonshot program which John F. Kennedy had started, which said, we choose to go to the moon in this decade because, among other things, this is not because they're easy, but because they're hard. The Sunshot program was started by President Obama, and the idea here was that we want to make solar energy or solar panels that you can put in your rooftops to be cost competitive with the energy that you get currently from the grid into your homes. And that uses fossil fuels, which is bad for the environment, right? So the goals of this program are this. So right now, if you want to install a solar panel in your house, it costs you about $3 per watt. That is the metric. $3 per watt, but you need many, many watts in your house. In order to be compatible with fossil fuels, you need to get down to $1 per watt. And that is the goal for the end of this decade. And I think we'll get there. And then you'll see a lot more panels installed in many places. All right, so just imagine if this were true. If this were true, then the cost would be the same for solar panels that you would have for the power that you get from the grid right now. It would create new jobs. It would create energy security because you don't have to get oil from a different country. So it creates security. And it's healthy because there's no carbon that's going up into the atmosphere, creating all the issues like global warming taking place, right? So this is the promise of solar energy. So let me just show you one example. I talked about panels going on your houses. But you can also have solar farms which produce electricity and supply it to the grid. So here's an example of one large solar farm in Germany. It's equivalent to 200 soccer fields and provides 42 megawatts of power into the grid. Just for size comparison, there's an Airbus A350 right there, and that's what a delivery van would look like, so it is huge. But the world's largest solar farm now is located in India. They started one in Gujarat. This one was 52 megawatts. This is going to be 1,000 megawatts. And it is going to save 8 million tons of carbon dioxide, which would have otherwise gone into the atmosphere. It'll prevent that from going. That's really nice. So now let's go to the next kind of way to create electricity from the sun, and that is from heat. So here what you're doing is you're taking the heat and you're converting the heat to steam and then to electricity, or you convert the heat into some kind of a fluid, and you put it into a fluid which can store the heat, right? So all of these ways in concentrated solar is to take the heat that you're getting from the sun, reflect it using mirrors into some focus. In this case, in the parabolic trough systems, you focus on this line, yellow line. This is a mirror. You focus it here, and you heat this fluid which is inside these red lines. It goes through a heat exchanger and creates steam and creates electricity, or you can store it in some sort of a tank where you can store these high temperature fluids that you've heated with the sun. Or you can have something which is called a linear mirrors. We've got linear mirrors, and they all heat, again, a fluid which is inside a tube over here. Or you can have a bank of mirrors like this, all concentrating the light on one point right here. So here's the sun. All these mirrors, large mirrors, they focus the light right here, and you put a fluid here, you circulate this red fluid, and so basically this fluid can either create steam and move a turbine, or you can store it and you can use it in the night as well. when there's no sunlight. And there's a dish system. In this case, you have a satellite like this, right? And it's concentrating all the heat over here, sunlight over here. And right here is there's a Stirling engine. And in fact, you're going to get a demo of that later on today. Basically, it's got a fluid which you've got a hot end and a cold end. And this fluid, this medium, it can be a gas or a liquid, which expands and contracts and moves and can actually create mechanical energy from heat energy to mechanical energy, which can then drive a turbine to electric energy. So this short video summarizes how concentrated solar thermal works.
Reflect it against a mirror. Focus all that heat on one area, send it through a power system, and you've got a renewable way of making electricity. It's called concentrated solar power, or CSP. Now, there are many types of CSP technologies: towers, dishes, linear mirrors, and troughs. Okay, have a look at this parabolic trough system. Parabolic troughs are large mirrors shaped like a giant U. These troughs are connected together in long lines and will track the sun throughout the day. When the sun's heat is reflected off the mirror, the curved shape sends most of that reflected heat onto a receiver. The receiver tube is filled with a fluid. It could be oil, molten salt, something that holds the heat well. Basically, this super hot liquid heats water in this thing called a heat exchanger, and the water turns to steam. Now the steam is sent off to a turbine, and from there, it's business as usual inside the power plant. The steam turbine spins a generator, and the generator makes electricity. Once the fluid transfers its heat, it's recycled and used over and over. And the steam is also cooled, condensed, and recycled again and again. One big advantage of these trough systems is that the heated fluid can be stored and used later to keep making electricity when the sun isn't shining. Sunny skies and hot temperatures make the southwest U.S. an ideal place for these kinds of power plants.
So, in fact, the world's largest concentrated solar thermal power plant just opened 2 days back. Can you believe it? Just 2 days back. This is a plant called Ivanpah. It produces 392 megawatts. This is what it looks like in the aerial view. It's got 300,000 heliostats, which are mirrors 7 foot by 10 foot in dimensions. And it avoids 400,000 tons of carbon dioxide going into the atmosphere. This is what it looks like. If you zoom into one of these things, all of these are mirrors like this, individual mirrors, not photovoltaic panels, just glass mirrors, concentrating the light into that one point. And this company is owned by Google. So they're, Google, you know of Google only as your web browser, but they are also doing things with energy, yes? So you can ask the question before we sort of come to the end here. Go ahead.
How high temperature will one of those systems reach at the top of one of those towers?
They go very high. Joanna, do you have a number?
At least 1,000 degrees Celsius. So
Can they go more than 1,000?
yeah, 1,200.
Yeah, so about maybe 1,200 degrees centigrade.
So it's molten salt. It's a salt up there that's
Yes.
capturing the energy.
Yes. So let me ask you a question before I let you guys ask questions. You can ask, why do we need to harness solar energy? Many people say you need to harness solar energy because fossil fuels such as gas and coal and oil will run out. But in fact, recent work in a paper that's come out recently has suggested that that's actually not true. We are finding more and more fossil fuels everywhere because we've got better ways to find them. And the Earth's been around for a long time, so there may be so many more reserves out there. So the real answer is that we want to use those. We want to use solar energy because it's clean, and it doesn't produce CO2, which results in global warming. So there's a quote from somebody in the Middle East which said that the Stone Age did not end because we ran out of stones. It ended because we transitioned to better solutions. So in case we can get solar cost effective, we would have transitioned to a better way of making energy and meeting our energy needs than what we are using right now. So let me just summarize on what I told you today. We started with the sun, and we said that you can have two ways of harnessing energy. One is taking the light from the sun, converting it to electricity. The other was taking heat and converting it to electricity. And I showed you various ways that you can do that. Now we're going to go and do projects, hands-on projects. Go ahead.
Is that heating? Is that like the heating? Like that the liquid that gets heated up? Is
Right.
it more efficient than solar panels?
Well, so there are solar panels which can go all the way up to 40% efficiency. The concentrated solar, the heat part, right? Most of those systems have efficiencies of about 20 to 30% even, except their cost is still higher. So what really matters is how much energy can you generate and at what cost. So both of them, both photovoltaics,
I mean, like with the mirrors.
right. So the mirrors have the efficiency of about, depending on which system you talk about. Some of the systems with the one with the Stirling engines, etc., the dish system that I talked about can approach 30%. Some of the other systems are around 20% efficiency. That's the amount of energy that's shining and they're converting, yeah? So the hands-on projects that you're going to do one project on solar thermal. You're going to make a solar cooker. You're going to concentrate the sunlight and produce heat. And the second is you're going to do a solar cockroach, which will move when because the solar cell will produce energy, and it'll have the cockroach moving around. You'll also get a demo of a thermoelectric generator and a demo of a Stirling engine. So what we're going to do is we're going to split you guys into two groups. Half of you are going to do this, and half of you are going to do this, and then you're going to switch around and do the one that you did not do. But before we do that, we also have for you something else. So those of you who are interested in learning more about solar photovoltaics, the semiconductor materials that we talked about, we can, instead of this regular photovoltaics, we can offer you an advanced photovoltaics in lieu of this. But we have a prerequisite there. You have to have had high school level physics or chemistry and the desire to want to know more, right? So all the people who meet this prerequisite and want to know more about solar cell functionality and how it really functions, what are the device characteristics, there are so many questions you can think about, and Jay is going to be working with you and telling you all about that. So here's what I can request. All those people who would want to learn about the advanced photovoltaics, stay here in this room. The rest of the people, we'd like you to all go to the cafeteria, where we're going to make you into two groups, one working on solar thermal and one working on photovoltaics. Yes? Quick question.
Yeah, the advanced photovoltaics.
Right.
What are you guys going to do? Is it something with that?
Right. But you need to have this high school level physics or chemistry because we have very limited time. Yes? All right, so let's do it. We are running out of time. Thank you.